Welcome everyone. Today we are at Stony Brook University having a very special interview with a very special guest today. Today we are interviewing Professor Abhay Deshpande, distinguished professor at Stony Brook University. Abhay is a State University of New York distinguished professor in Department of Physics and Astronomy at Stony Brook. He also serves as a Director of Science for the Electron-Ion Collider at Brookhaven National Laboratory. In addition, he is the founder and director for the Center for Frontiers in Nuclear Science. Abhay, welcome to the show.
Thank you. Thank you. Glad to be here.
Now let me start with some tradition question we ask to all physicists. We all can relate to physics. Everyone has his own special story about we want to do physics, where you're coming from. But every time I ask this question about what's physics mean to you, I get a different answer. So I want to hear yours. What's physics mean to you and what motivates you to do research?
Well, the reason I got into physics originally when I was in high school or late high school was when I realized that I was very bad at memorizing things. And biology, botany, zoology, those fields, the way they were taught in my school, needed a lot of memorization.
I can relate.
And when it comes to physics, we were learning Newton's laws, and there was this professor who was explaining how you only need to know the initial velocity and an angle of a projectile, and the rest of it was governed by a simple physics law of gravitation.
Yep.
So you could derive everything, you could figure out everything on your own. You didn't have to remember things. And that was a transitional day for me. In the morning, I had this botany class where the teacher told me you had to remember 4,000 Latin words. And in the afternoon, the professor told me, you don't have to remember anything. You just have to remember one law of physics and play with it. And that was the way I got attracted to physics for the first time.
This is very interesting. By the way, this is how many of the physicists have been, say, when they would try to tell the story of physics,
Yes.
They thought about it this way, because first Aristotle think about trajectory problem, it comes to the ground because of its own nature.
Yeah.
And then it was like later after that recognized the concept of momentum conservation. And then, so I can relate to the fantastic experience of yours.
Yeah. And then there was this book by Steve Weinberg about the first 3 minutes, which was at that time when I was growing up in 1980s, a brand new book. And it has fascinating description that was accessible to a non-expert like me in college and undergraduate college or even high school, told us how we think the whole universe began. Our knowledge of Big Bang was much more limited at that time.
Yeah.
But the evolution of the universe since then made a lot of attractive comments, and that was really interesting to study. And so I read that book. I think it was probably the first book that I read from beginning to end without stopping over a summer, and was fascinated by it. And that's when I realized that that's the direction in which I probably want to go.
It's about undergraduate time?
Sometime around, what in India was a junior college was 11th and 12th grades.
Oh, okay.
In the US, it is more like a high school, last 2 years. And that's basically when I decided that I think I was going to go in that direction.
And you studied physics in India there?
I studied physics undergraduate in India, yes. I was an undergraduate at University of Mumbai, or Bombay as it was called. And then I did my undergraduate master's degree before I came to the US at an institute called Indian Institute of Technology in Kanpur, which is in northeast of India.
So and your master's was related to particle physics?
No, actually, there was a very general master's. There was no specific direction. We had a all host of topics that we had to study in the class, and there were experimental programs there. But I had to choose a major project during the last year, and I had to do some research. And for some reason, I had selected, for the lack of experimental opportunities in high energy or nuclear, I think I chose only because of that, a project in condensed matter where I was creating thin films on various substrates. So I learned that, sputtering and all these kind of things. It was a very bad lab. Nothing worked.
I can imagine thin film require a lot of technology and
Yes. Well,
get contaminated all the time easily.
it is true. That is true. But if the sputtering works, right? In our lab, even that was not working. So,
so the most
getting
basic
a
thing
bag,
is not
yes. So the question was whether I could fix it and then use it. So that fixing then took all the furnace had to be fixed and everything in that lab had to be fixed. So that was a real tough experimental start to my career. And I hated it. I did not do condensed matter or solid state physics afterwards.
Oh, which is surprising me. You're now one of the most successful experimentalists. So how would the transition happen to particle physics?
So I think at that point I had done enough of advanced undergraduate courses to realize that I was going to go in the direction of either nuclear or particle physics. But as it happens to most people in India, because they don't have a direct large exposure to experimental instruments in their universities or in the vicinity, most people think of physics as a theoretical topic. Most of my professors were theorists. So they would teach also from theoretical perspectives. So I thought I was going to be a theorist. And I was doing well in school and in my college at master's degree level. And when I applied to graduate schools, one of my professors noted particularly that I was also very good at experiments. And he told me that India needed experimenters. There were not too many of them. In general, he said, world needs more experimentalists because physics is an experimental field. You observe first and then try to explain. Most often, that's how the direction is.
Yes.
Not always, but most often. So that was an indication to me that I should explore. And when I started exploring as a young graduate student, I really liked it when I took it seriously. And then I continued in experimental physics. At that time, I was a particle physicist. I mean, formally called particle physicist.
So where did you start? Which university or institute?
So I came for my PhD at Yale University in New Haven, Connecticut. And so that's where I started my career in the US.
One of the strongest groups.
Correct. And they had, but I was in the particle physics group, in rare kaon decays. So my thesis was on rare kaon decays. 2 decays that I measured were of the order of 10 to the minus 8, 10 to the minus 10 branching ratio.
That happens at CERN?
No, at Brookhaven National Laboratory. Yeah.
Okay.
So I used to drive to Bridgeport and take the ferry.
Oh, okay. So every driving every day from...
Not every day. I stayed here at Brookhaven for 8 months during the experiment. And otherwise, I would just drive from New Haven. It was a very fast drive, 2.5 hours it takes to go to Brookhaven. The traffic conditions were better then. Nowadays, it might be a little bit more. And then we had a professor in our group who had a flying license and had a small plane. So very often I used to fly from New Haven to Brookhaven.
So you go to work on plane.
Yeah, it would take us 20 minutes. It would take us 20 minutes to the airport from Yale, and then 20 minutes or maybe 25 minutes in the air because of the slow, takeoff and land. And then he would park the car, and then somebody would pick us up from the airport next to Brookhaven. And that was 10 minutes. So within 45 minutes, we were from the physics department at Yale to the physics or the AGS at Brookhaven.
I can imagine the experience just telling that you was flying to work. It
was fun. It was fun.
And then you graduate from Yale. And your postdoc was...
So I graduated from Yale, and it was a funny story. First, I thought I would graduate 2 years before, or 1.5 years before I actually did. I had an offer for a postdoc, which was partially on neutrino physics and partially on SSC.
Okay.
And within about 3 months of getting that offer, SSC was killed. So my job just disappeared.
I think many of our audience will not relate to SSC.
Yeah, SSC was the superconducting super collider that was supposed to be built in Texas, Waxahachie, Texas, which was of the order of, if I remember right, about 1.5 times larger than the current LHC, the Large Hadron Collider at CERN.
It was supposed to be the largest
one, and it proceeded to quite a long through its project. The tunnels were dug, and it was quite advanced, the project itself. But due to cost overruns and changes in the government, it was eventually cancelled. However, that was the end of my first job offer. And then I had extra time, and one of my colleagues in the group, in the collaboration, the collaboration was a high energy physics collaboration with only 21 collaborators.
Wow.
And there were 4 students. 2 had already graduated by the time I joined.
Okay.
And 2, we were you 2 young ones. One was me from Yale and one from University of Washington. And that person decided to quit physics at that time, or quit high energy physics, and move to something else. So there was this one physics topic that could not have been covered because we lost one graduate student. And since I had just received an offer and lost it, my advisor said, hey, why don't you just do that analysis too? You have some time now and you will finish it in next 6 months. Of course.
It took 6 months.
It took 1.5 years. But it was a good paper, I thought, and I learned a lot. I was a lot more independent during that time. I was not treated as a postdoc, but I was essentially working as a postdoc.
More independent in working.
So that's how I graduated. That's when I graduated. And by that time, I had a second offer, was from CERN.
Okay.
And it was a CERN fellowship, and I had applied for it from New Haven. Only after I got it and they started doing the paperwork did they realize that they had made a mistake, that they had assumed I was an American citizen. So CERN fellowships were given to American citizens and the European citizens. But for Indian, I was an Indian citizen then, it had to be an associateship. So suddenly they realized when I sent them my passport that they had made a mistake. But they couldn't fix it because there was only one fellowship in Asia that year, and that had been given already. So they could not take it back. And so this wonderful professor from Yale, who came to know about this situation, Professor Vernon Hughes, who wanted me to work with him for a long time. And I actually was planning to work on his experiment at CERN anyway, through the CERN fellowship. So he stepped in and he made a few phone calls, and the way it worked out was that there was a joint CERN-Yale fellowship for the first year, and then it converted into a Yale fellowship afterwards. So I worked for Yale for the next few years with Vernon Hughes, but stationed mostly at CERN and in Geneva. And that was a transformative time. I think I really loved that time. Yeah,
it's a very interesting story, because usually when we hear stories how people become who they are those days, we forget how much it was hard sometimes. And I wouldn't call it a failure, but it's a bunch of
mistakes, right?
Yeah, it happens all the time. You find this job and things goes bad.
Had to happen, yes.
Exactly.
And it was during that time that I was working with Vernon and working on that particular experiment at CERN, which, he helped me overcome the problem of getting a job because of the failure of the administration. That the idea of everything I've done since then started during those 4 years with Vernon. So it's really a crucial mistake that happened twice.
Yeah, and sometimes it shapes your future, not only that, but give you different experience. Sometimes experience that you never expect to have in your own.
Yes.
Which leads me to my second question, actually. With all of this experience, usually we get a question like, what the hell particle physics want to do with the world? Building bigger and bigger machines, having the small colliders first give me, an accelerator, linear one, then we turn them into a circular accelerator, and then we turn them into colliders. We go to relativistic heavy ion collider here at New York, and we go to the Large Hadron Collider. Then we're now going to be upgrading LHC at some point and having the Electron-Ion Collider at United States.
Right.
So what is with the experimentalist in particle physics and big machines? Like, why are you guys heading always toward this costly machines?
Well, it's not that we want to go to costly machines. It's that the machines are becoming more and more expensive. I think one of the reasons why high energy frontier has now people realize that I don't know that people will think about another large collider after the future circular collider, which is already reaching the limits of 100 kilometers, 100 TeV machines. This is becoming financially very difficult. And the reason why it is becoming financially very difficult is because we are relying on acceleration of particles based on technologies that are about 50 years old. So if you really want to push it without doing any innovation, then you're always going to be limited by the length of the machine, either circular or linear. So I think there is a realization amongst the community, and I think there is now effort starting to discover novel other alternative methods of acceleration, like the plasma wake field acceleration and novel ideas that have emerged over the last 15 years. When they will realize as a practical machine is another thing, but I think there has to be a lot more investment in such particle acceleration ideas to make sure that future accelerator become affordable and still go over the energy frontiers that we want to go. You mentioned Electron-Ion Collider. That is not an energy frontier. That is not a cost frontier. There, you do not want to, like the large colliders want to go into smaller and smaller distances to look for smaller and smaller object. Currently, we think quarks and electrons and muons, the fundamental particles of the standard model, are the smallest amongst them. We have not seen a substructure of quark yet. And to some extent, looking for physics beyond the standard model, you're looking for some kind of a substructure beyond what we know. And for that, you need the highest energy. The Electron-Ion Collider is a different beast. There, you're not looking for substructure of the quark, but you're looking for a collective behavior of the quarks and gluons inside hadrons. So a big fraction of the internal volume of protons, how the quarks and gluons behave there is of interest. So since the distance scales are much larger than the size of the quarks and the distribution of gluons, we don't need the energy frontier, but we want to measure them with enough detail that you need a very large intensity. So we need a large number of events that should come out of the photon quark scattering or photon gluon fusion. And that takes an intense machine, not the highest energy machine, the luminous machine. So I call it the intensity frontier or the luminosity frontier, whereas the LHC and the other higher energy machines are the energy frontier.
So if I want to say it in a different language, way dummier than anything I can ever imagine, that basically we're building a new glasses. There are two kinds of glasses right now. One that we need to change the frame and the lenses. And the one we're building over here, the EIC, is we want to focus on the lenses, how clean we can see.
Yeah. I think we need to see the collective behavior.
Yes.
Right? And you need to understand
and the high resolution. So that's we need to focus on the resolution.
But the distance is not the issue there, right?
Yeah.
It's the many pixels in your picture.
Yes.
Together will form the understanding or lead to the understanding.
Yeah. I like your idea about the technology, because it's where we are right now is using the 50 years old technology. And if we want to go beyond that on the energy level, like speaking about string theory or quantum field, if we can discover any of those in the lab, that's mean we're speaking about way stronger accelerator than what we had, and that will need a breakthrough in the
yes, that
in the
will be a new
accelerating
technology.
field.
And I think we are due for it. I think it's I think we have to go in there. We will be forced. Otherwise, the high energy frontier will somehow disappear in the more controlled way. You can still do cosmic ray science, which gives you today even the most energetic particles, and then you could study particle physics using those. But it is not a controlled way of doing it. And in the colliders and experimentalists are actively controlled areas.
So if you look to the field of particle physics today, if you want to make a chart what we have achieved, and that maybe will lead us to the next part about the electron ion, but where do you think we are currently in the landscape of particle physics?
Well, I think looking at it from the electron-ion collider point of view, I like to give an analogy. We understood in the 1950s and 60s very precisely how a photon interacts with the electron and vice versa. We understood it very well. But when millions of electrons start interacting with millions of light photons collectively together, a new field of electrodynamics is formed, what we now call condensed matter science. And that led to the understanding of the structure of the diode, the working of a diode, the transistor, and the transistor made possible the electronics revolution, for which we are very thankful for.
Technology.
How many Nobel laureates have emerged out of the field over the last 50, 70 years since the transistor came into picture, into solid state devices. All of that you should think back on. In the high energy physics, particularly in the context of EIC, I feel that we understand the interactions of gluons and quarks at that individual level, something similar to what we had before 1950s for the electroweak.
Yeah, of course.
Now we are entering an era in which a huge number of quarks and huge number of gluons are able to be studied collectively together. And when we say that the proton is made up of millions of quarks and millions of gluons, and somehow magically they know how to create the exact mass of the proton and the exact spin of the proton, that collective behavior that finally results in the properties of the proton, that thing is a transition of QCD, quantum chromodynamics, into its collective behavior. So it's the condensed matter-like transition that is happening. And I think the electron-ion collider will face that problem and is going to address that problem very directly to see how the origin of mass can be understood, how the origin of spin can be understood from these interactions which are chaotic and diverse, to say the least. How somehow they all know exactly to add to the proton mass is going to be told to us by the future experiments. And this is where the field of at least particle nuclear physics is, in my opinion.
Is heading, yeah. That's very interesting, how a general picture of where we're heading in the field of particle nuclear physics and why we need a new accelerator like the Electron-Ion Collider. As one also of the leading scientists in the Electron-Ion Collider, you had been always said it's a dream that came true.
Yes.
So I want to hear about the story, actually. I think it's an interesting story where the idea came from, how you guys drive that project from just an idea in a mind of like postdoc or a very fresh professors into now a real project that's, I think our generation and the next generation will work.
So the original idea for trying to build a polarized collider was a simple limitation of a fixed target experiment. If you have a fixed target experiment, a beam comes in, you put in a large energy into it, and then comes and hits the target. The target, in our case at CERN, was a proton or a deuteron, meaning neutron, and we had a large energy muon beam. And by simple kinematics, you can figure out that in that scenario, you can go to a certain value of minimal momentum of the quarks and gluons that you want to explore. There is no more you can do. But if you do instead of a collider where both particles are moving, then for much less effort, meaning cost of energy or lower energy beams, you can do equivalent or even better. So what we were trying to do at that time in 1995, and look at the data from the spin-muon collaboration experiment at CERN, and we're trying to extrapolate to understand how the spin structure function of the proton looks in the very low momentum fraction region. And what we found was that the theory could not help us beyond certain models. And the model was a straight line, a Regge kind of extrapolation that said that you had to just extrapolate to zero. That was the best you could do. And every experiment in the field at the time was doing exactly that. And then theory developed around 1995, 96, and for the first time, a next to leading order perturbative QCD calculation for the structure of the proton came up. Once that came in, I started comparing that extrapolation with what we had before. And there was a huge discrepancy. So everything that every experiment at that time had published in terms of what that extrapolation should look like was all completely wrong, according to the next to leading order perturbative QCD. That was a big shock to everyone was involved. However, there was no way to experimentally check it. So I quickly realized that to go and measure it in that region where those two predictions differ very significantly, the only way to do that was to do with a high energy collider. And that's when I first promoted that we need to go into a collider. The first initial idea was to go to Hera, an EP collider that already existed, but an electron beam was already polarized, the proton beam was not. So my first effort at that time was to go and try to polarize the proton beam. And there were a large number of people who were helping us on accelerator side. I was going to use the H1 and Zeus detector and build the community to do the spin physics there. And the collaborations existed. So I could have done it at that time. The problem was there were some technical large difficulties in getting the proton beam polarized. And those difficulties prevented us from going very fast forward. There was a proposal to put in some nuclei in it, but that too was given a very short time by the managers of the lab at the time. They said, we don't want to run this collider for more than 3-4 years. You have to finish the program by that time, because they had a dream to build the next linear collider in that area. So they wanted to use all those extra infrastructures to move in that direction. They wanted to go quickly from there to something else. And unfortunately, they lost the bid, but they also stopped us from doing it. And that's where, when I first moved to Brookhaven National Lab, came to the US back, and realized that you had the nuclei, all the nuclei, and you had polarized protons at RIC.
You need the electron.
Then you need the electron. And so my friend Raju Venugopalan, who was also a very junior faculty at the time at Brookhaven Lab, and I was just coming in as a RICEN fellow at the RICEN Center, RICEN BNL Research Center. And so we started talking to each other and got a lot of encouragement from Vernon Hughes and Larry McLaren, who was a theorist, who was the head of the theory division there, and also the management there. Peter Paul was the interim director at that point. And so that group helped quite a lot locally. And we were encouraged, and we started a small workshop on the Electron-Ion Collider. And since then, since most people who were doing this kind of physics around the world realized that the bigger problems were in this low momentum fraction region, it was very natural that they all supported and joined the forces. So what we did right was to gather all those people together. I mean, although we had the idea originally, there were other good ideas coming through. So all of those people came together. There was a idea that was being pushed by the MIT group to build a small collider at the Bates in Boston. There was a group at Indiana University that wanted to use the IUCF as one of the beams. So ideally, they wanted to collide the Bates beam, electron beam on the IUCF proton beam. right? And that was really what they wanted to do. And they would have done a nice small experiment. Here we were, Raju and myself also, we were naive, we were young, we were naive, and we were saying, oh, we should go for high energy. We already have the RIC. And initially, everyone thought it was too ambitious an idea for us.
At what year was that?
This was in from 98 to 2000.
So Rick was still young and fresh.
Rick was not on yet. It started in 2000.
Yeah. Okay.
Yeah. And the first workshop we held on the Electron-Ion Collider was in 1999. So even before Rick started.
Structure just Rick with in a structure part. I think collaboration forming.
No. Collaborations were formed.
Oh, okay.
The detectors were almost built. The detectors in Rick were built from somewhere around 96 to about 2000. And this we were talking about in 1999, the last year of construction. So a lot of people thought it was a distraction. It was really a distraction. They didn't like the fact that some younger people were coming in with an idea that would, and I think it happens. It's natural. Some others had spent a lot more time on designing and constructing Rick, and suddenly there was a alternative proposal, or not alternative, but we never thought it was in competition. We always thought it was a sequential thing to do, future. However, at the same time, the timelines given to us to realize by the experts in accelerator science were very ambitious. They would tell us that we could probably build this in 8 years and run the experiments in 2008, for example. And I have slides to show that. I mean, there were slides that I used to use then at that time promoting the idea. And it would not have disrupted the RIC program at all. It would have let that continue. But in addition, there would be an interaction region in which you could have an electron-ion collider.
Okay.
Yeah. So that was the idea. So it was never to interfere with the RIC program.
The RIC program, yeah.
But it is a disruption. I mean, to set up a new IR, to set up a new detector would have taken time off. So there was some skepticism. Eventually, I think the way this whole thing worked out, I think we have a much better machine now, a design. A lot more people joined. There was a proposal from Jefferson Lab that joined the effort. And I think because of the two labs competing, the overall design of the project is much better now than what we had now. The parameters are much more ambitious. And I think because of that, we can do a lot more physics than what we wrote in our 2002 proposal for the first time. I mean, the first time we all came together, the MIT, Indiana University folks, and we at Brookhaven came together and collectively went after a machine like what we have now in EIC at Brookhaven. I think it was very important that collectively we made compromises and said, okay, let's go for one machine, but go united. And I think that was a very important decision we made, and we made that at MIT in the year 2000. And then we worked for the next year and a half preparing for the long-range plan. And that worked out very well. We already got a mention in the first long-range plan that we went. We also then continued that work for the next one and another one. And finally, it took us 3 long-range plans of the NSAC to get finally a recommendation that the project should go ahead as a construction project. Yeah,
it's very important, Trev, because it tells the future generation how they should move.
Yes.
Yes. And it says also that's never too early to think about what you want to do in future, because we reach the end of the programs anyway, sooner or later. That's what happens.
Yes.
So I think about the part, what will be the timeline? We have a much younger scientists are watching, and what's the timeline for the EIC to have the first collision happening?
So we are currently in the final design periods of the accelerator as well as the design. We are building the collaboration, but the collaboration is there is secure enough, but the funding for the detector has to be realized. The funding for the accelerator has to be realized. In the US, this is an annual a negotiation with the government to get the money and assign it for construction. For detectors, about 30% or 25 to 30% of the detectors will be built by our collaborators who are not US funding agencies. So that kind of a setup is now being negotiated with various countries around the world, and we are all optimistic that that will happen and will get finalized in the next year or so. We were very happy to hear just yesterday that the United Kingdom finally approved a $75 million project proposal for EIC. So that money is now, that's the first one that got approved, non-US contribution.
That's great. Yeah.
And that's wonderful. That's both for accelerator as well as for detector. And such discussions are now going on with other funding agencies through their respective users, through their respective EIC users and EPIC detector collaborators. So all that is going on now. I have expectation that technically driven timeline for this starts its construction late 2025 or early 2026. That will go on until about 31, 32, which is when the beams will start circulating. At that point, most of the detector, if not all, should be there so that you can turn it on and start testing. But at the same time, you can give feedback to the accelerators when it run it. So the first year or so, it will be only testing the EIC operation, and that will be driven by the accelerator scientists. We physicists, we will not, experimental physicists, will not have a say in what they should run. So once they become more confident about handling the machine and start ramping up the luminosity and the polarization studies, that's when we should be ready for physics. And I think that will go to happen 2 years down when the first collisions happen. So 2033 is approximately the earliest we can think about physics-related collisions. 2031 are the earliest engineering collision, what I call engineering. So we have about 10 years from now onwards. There's a lot to be done during those 10 years, both on the experimental side, but also theory side. Lots of theory has to be developed, made it precise, calculations need to be there in place. So there is a lot of work cut out to be done.
A lot of physics to be discussed and discovered. I think that's pretty much interesting, because now we covered even the new machine coming. And by the end of that, I would like to ask you if you would like to give an advice for our coming generation or younger students. So this will be broadcast in Arabic, it will be translated. But, Egypt has an EIC group.
Yes, I'm delighted to know that, yes.
What you would like to say to younger generation here?
Well, I think I see the generation that is coming in Arabic world right now is probably equivalent to what I was as well. There were not local facilities for doing things that I would have liked to do, especially these kind of things. But having the idea and liking and pursuing it, no matter where I had to go and get involved to do that, I think it should be open. You should keep the mind open. Be attracted, be honest to the science and your intuitions and also your liking. And pursue what you believe is the right thing to do. No matter what everyone else might tell you, I think that persistence is needed. It doesn't mean that you should ignore the advice of the wise and the senior. You should acknowledge that. But at the same time, at the end, it's your decision. And if you can just manage that and learn from all the mistakes of the others and ask them what mistakes you made, don't just assume that there were no mistakes made. And there are people who will tell you many mistakes that come their way. And I think it's good to not repeat them. So for that, at least talk to the elders, talk to the senior people, and then go forward. I think science generally around the world is open enough to accept people from everywhere. So it's a borderless community. And I think it would not be too difficult to get help when needed for people from Middle East, people from Arabic countries, particularly now that Egypt is going in this direction as well. So just be optimistic and pursue your dream.
Thank you so much, Abhay, for accepting my invitation, and thanks for the interview. I really enjoyed, and I think our audience will enjoy it too. Thank you.
Okay, thank you.